just in case we have a few that don't join. All right. Let me go back to PowerPoint. So what we're going to do today is we're going to start our discussion of complex numbers. And we need this set of numbers because we need them for the next section. So far, all we've done is solve linear equations. And linear equations are those equations where the variable, the largest power on the variable is 1. But we need to be able to solve equations other than just linear equations. So in section 1.5, we'll start looking at quadratic equations, and then we'll look at other types of equations. So we need to be able to deal with square roots, because quadratic equations, the quadratic formula, and no, you don't have to memorize this right now. We'll talk about this again on Thursday. But the quadratic formula contains a square root. And for those of you who've seen that in the past, you might or might not recognize that formula, but it contains a square root. And because it contains a square root, we need to be able to deal with square roots. And not only do we need to be able to deal with square roots of positive numbers, we need to be able to deal with square roots of negatives, because that b squared minus 4ac, that expression underneath the square root symbol, that might be a negative number. And we need to know how to deal with those. So what we're going to do is first we're going to define what complex numbers are. And they're numbers. They are numbers. That's all they are. And since they're numbers, we can carry out the 4 arithmetic operations on those numbers. We can add them, we can subtract them, we can multiply them, we can divide them. And we're going to do that. And then we'll look at some specific square roots and how we can use the fact that we can simplify square roots. We can do that first. And second, we can now deal with the square root of negative numbers. All right. Okay, so I think I railed on this to your class one day, but if I look at b squared, and b is a real number, and we're going to define real numbers specifically in just a second, but what I've already said is that if you have a number line, numbers to the right of 0 on the number line are positive, numbers to the left of 0 on the number line are negative. But there are an infinite number of points on this number line. Every point on this number line is a real number. So if you can plot it on a number line, it's a real number. If it's on the number line, it's a real number. So if you can plot it on this number line, it's real. Or if it's a point on this number line, it's real. Okay, so that's how we represent the set of real numbers. It's every point on a number line. So if b is a real number and you square it, it must be positive. You cannot square a real number and get a negative. You can't do that. There is no real number that when you square it, you get a negative. So if I square 2, that's by definition 2 times 2, which is 4. If I square negative 2, now I'm going to put that in parentheses. And I put that in parentheses because I am telling you that the number that I'm squaring is negative 2. So I need to put that in parentheses to make very, very clear that the number that's being squared is negative 2. And when I do that, that's negative 2 times negative 2, which is again 4. Because when I square a number, I multiply it times itself. When I multiply a positive times a positive, I get a positive. When I multiply a negative times a negative, I also get a positive. Now, the difference in this and this is pretty important, because the first one there, the first line says take -2 and square it. The second line, as soon as I remove those parentheses around the -2, that has a whole different meaning. So what does that mean? That means to take the number 2, square it, and change its sign. So whenever we have a negative outside of a real number, that means to take that number A and change its sign. So in this case, you're going to take 2, you're going to square it, then you're going to change its sign, and that's going to become -4. All right, so there is a difference. Sorry, whenever I'm in Zoom and I get an internet connection is unstable, I pause a minute. Okay, so what's the moral of this story? The moral of this story is there's no real number you can square and get a negative. Well, are there numbers I can square and get a negative? And the answer is yes. And that's why we define imaginary numbers, because there are instances when I need to square something and get a negative value. All right, so let's talk about number systems. So my granddaughter is not 3 years old yet. She's going to be 3 in April. But she has, in the past, I don't know, 9 months since her second birthday. I mean, it's amazing the development of a child from their second birthday to the third birthday. And I kept telling her parents, my son and daughter-in-law, be patient, be patient, be patient. Because 2 is a really difficult age to be, because your intellect wants you to communicate, but your verbal skills are just not quite there. And I know that's why a lot of parents teach their children sign language, because they can sign their issue and not have to verbalize it. It's really hard for a 2-year-old to verbalize. And somewhere in there, they start verbalizing, and one of the first things they verbalize is numbers. It's an amazing thing that at age 2, children understand numbers, and at age 52, we say, I don't know, math is hard. So I think I've talked about this in class. Something happens between age 2 and age 52. But if you ask my granddaughter how old she is, she holds up 2 fingers. Now, I'm not sure that she understands the concept that 2 means 2 years. I'm pretty sure she doesn't. But she does understand counting. And she understands if she's got a series of objects, she can count how many she has. She actually understands that. So if I tell her to start counting, she starts counting. And where did you start counting at? You start counting at 1. So my 2-year-old granddaughter, I say, count to 10, we'll see. And she says, 1, 2, 3. So she knows how to count to 10, and so do you. So the counting numbers, we give a name in mathematics, and we call those the natural numbers. So the natural numbers are the numbers that we count with, and they're a very important number system. They're the number system that we start with. Computer scientists use these numbers all the time, because when they write programs, it might be important that they count. So natural numbers are not unimportant. They're very important. Now, you'll notice some things about this. The natural numbers are a set of numbers. So we do a couple of things to denote that this is a set. So first of all, the braces. If we have braces around a set of numbers that are written in a roster, so this is a roster of numbers, which means just a list. That means this is a set. This is a set of numbers that starts at 1, goes to 2, 3, 4. Then we have a comma and a dot, dot, dot. That dot, dot, dot has a name. Here's your Jeopardy word of the day. No, you're not going to be tested on this. It's called an ellipsis. And does anyone know what the ellipsis means when you have it at the end of a roster? You can type that in chat if you know what that means. No one willing to guess? What's that ... mean? It means that those numbers continue on to the right, correct? So if you're counting, you count 1, 2, 3, 4, you can count to 5, 6, 7, 8, 9, 10, 11, 12, etc. So those numbers continue on to the right indefinitely. They continue to infinity, if you will. Okay, so that's the set of natural numbers. Now, the next number that we add to this set to get a new set of numbers takes a little while for us to discover its meaning. And by the time we're adults, we understand the concept of zero quite well. If your bank account balance is, you have no money in your bank account, we understand the concept of zero. Or if you open the cookie jar as a child and you see there are no cookies in the cookie jar, then you understand the concept of zero. So if we add zero to the set of counting numbers, we get another set of numbers that we call the whole numbers. So the whole numbers are the counting numbers and we add zero to those. Again, we list the whole numbers as a roster, just a list of numbers with an ellipse on the right-hand side of that to show that those numbers continue on forever. Now, if I look at this set of numbers, the whole numbers, I can see that contained inside the set of whole numbers is the set of natural numbers. So what we say is that the set of natural numbers is a subset of the set of whole numbers because the natural numbers are completely contained inside the set of whole numbers. So they are a subset. All right, so the next set of numbers we need to be able to describe what happens when something's to the left of zero or below zero. And you could talk temperature, or you could talk your bank account again. If you overdraw your bank account, the concept of negative numbers to the left of zero, unfortunately, it becomes very apparent very quickly. So we need to add negative numbers to our set of whole numbers, and we're going to get a new set of numbers. So the whole numbers plus the opposites of our natural numbers gives us the set of integers. And the set of integers is the whole numbers with the opposites. Now, zero is not a signed number. Zero does not have a sign. It's not positive, nor is it negative. So you have zero, the set of whole numbers, the set of natural numbers to the right, and then to the left of that, you have the opposites of those natural numbers. So the opposite of 1 is -1, the opposite of 2 is -2, etc. And again, you see that we have ellipsis on each end now to say that we can continue to the right and to the left indefinitely. So numbers can get smaller and smaller and smaller as they go to the left, and larger and larger and larger as we go to the right. And again, looking at the set of integers, you can see there is the set of natural numbers. So the set of natural numbers is a subset of the set of integers, as is the set of whole numbers. So whole numbers and natural numbers are subsets of integers. All right, so the next set of numbers we need is a set of numbers that helps us deal with fractions of wholes. The reality of the world is that very seldom is anything a whole. More often than not, a measurement or whatever is a fraction of a whole. If you go into your bank account right now and you look at your balance, your checking account or your savings account, chances are the balance in that account is not a whole number. Maybe it's $432.27. So frequently we deal, especially when we're talking about money, we deal with fractions of a whole. We look at cents of a dollar, parts of a dollar. right? So what we do is we introduce a set of numbers that deals with the parts of a whole, or the ratio of two integers. So what we do is we define a set of numbers where the numerator and denominator are both integers, and we can't have the denominator equal to 0. So what we call these, since they're a ratio of integers, we call these the rational numbers, ratio rational. So numbers that can be written in the form a over b, a divided by b, where a and b are both integers and b cannot equal 0, are the set of rational numbers. Now, every integer is a rational number because every integer can be written as itself over 1. So -4 you can write as -4 over 1. So every integer is also a rational number. Now 5 is 5 over 1. Okay, so again, the integers are a subset of the integers are a subset of the rational numbers. I'll spit it out. The whole numbers are a subset of the rational numbers, and the natural numbers are a subset of the rational numbers. So any number that you can write as a fraction is a rational number. Now, talking about decimals, this means that the decimal either terminates or it repeats. So if you have a decimal, oops, that's the highlighter. We don't want that. Get my pen back. So if we have a decimal such as 0.25, that is a terminating decimal, 0.25. There are no numbers to the right of the 5. Since that's a terminating decimal, it can be written as a fraction. So if a decimal terminates, you can write it as a fraction. As a matter of fact, that's 1 over 4. So that is a rational number. If it can write it, you can write it as a fraction, it's a rational number. Now, if the decimal repeats, that's also a rational number. So the way we denote that, we have 0.3, and we put a bar over the top of the 3. So what that means is 0.3333, continuing on forever. But ellipses in there. So that means the 3 repeats indefinitely. So if that's true, if the decimal repeats, you can write that as a fraction. I'm telling you, you can. And that, as a matter of fact, is 1/3. So if a decimal terminates or it repeats, it's a rational number. So are there numbers whose decimals do not repeat and do not terminate? And the answer is yes, an infinite number of numbers whose decimals don't terminate or repeat. So what name do they give them? It's like, just, can we pull one out of the hat? So if numbers you can write as fractions are rational, numbers you can't write as fractions are irrational. Seriously, I think half the time they name things as a joke. So if you can't write it as a fraction, it's an irrational number. And there are an infinite number of irrational numbers, many of which you are familiar with. The number pi is an irrational number because, as far as we know, the decimal never terminates or never repeats. As many hundreds of thousands of places they've estimated pi to, 100,000 numbers to the right of the decimal, it's never terminated and it never repeats. So we consider it to be an irrational number. The square root of 2 is the same. If you take your calculator out, you can get a decimal approximation to the square root of 2, but you can't actually write it as a fraction. Cube root of 9, or the number e. E is called the natural number, and we'll talk about it quite a bit in chapter 4. So e is called the natural number. And again, it's just a number. It's approximately 2.71, that number. But as far as we know, it's never terminated and it's never repeated. All right. So now we have these 5 number systems. We still haven't got to the real numbers yet. So if we take all the numbers that can be written as fractions and join that with all the numbers that can't be written as fractions, so we take the rational numbers and join those with the irrational numbers by a union. It's called a union when we take the 2 sets and kind of stick them together. join them together. If we union the set of rational numbers and the set of irrational numbers, we get the set of numbers called the real numbers. So the real numbers, and you can see that U there, are the rational numbers unioned with the irrational numbers. And as I described earlier in this class, the set of real numbers are every number that you can plot on the number line. Or if it's a point on the number line, it is a real number, guaranteed. And every real number that you square will be positive. You cannot square a real number and get a negative, because when you square a number, you multiply it times itself. So when you multiply a positive times a positive, you get a positive. When you multiply a negative times a negative, you get a positive. So when you square a real number, it will be positive. Okay, so here is an illustration of the set of numbers that we've talked about. Starting with the innermost box, the set of natural numbers, the numbers that we count with. We add 0, we get the set of whole numbers. So the natural numbers are a subset of the set of whole numbers. We add the opposites to the whole numbers, we get the set of integers. So natural and whole are subsets of the integers. We write the integer numbers as ratios. When we write the integers as ratio, we get the set of rational numbers. So all the previous number systems are subsets of the rational numbers. But then we have a whole set of numbers that are not rational, the irrational. So that's a separate number system to the rationals. And when we join those together, we get the set of real numbers. Okay, so if we have real numbers, we have imaginary numbers. And I kid you not, the reason they call them imaginary is derogatory. So a couple of mathematicians named Euler and Gauss said, we need to be able to deal with the square root of negatives. That is not a real number. And it's not a real number because what does square root mean? The square root means what number do I multiply it times itself to get the thing underneath the square root symbol. So what number, when I square it, I get -16. Well, no real number, because you can't square a real number and get a negative. So it's not real. So what Euler and Gauss said is, we still need to be able to deal with this because it happens all the time that we get the square root of negatives. Remember when I wrote the quadratic formula on the first slide? You have a square root, and underneath that square root, you have a real number. And that real number may be negative. There's no reason why it can't be. So Gauss and Euler said, let's develop a number system where we can deal with the square root of negatives. And other mathematicians scoffed and named them imaginary, because if they're not real numbers, they don't exist. Well, they do exist. So what they defined is that there is this thing called I, and that is the imaginary unit. Just like in real numbers, the number 1 is the unit number. In imaginary numbers, the unit I is the unit. It's the imaginary unit. And it's defined to be the square root of -1. So the imaginary unit I is defined, by definition, it is the square root of -1. Now in mathematics, if it's a definition, you accept it to be true. You don't try to figure it out or ponder it or whatever. I mean, some, like my son, he tries to figure it out. But if I define that for you, that's what it is. So I, the imaginary unit I, is the square root of -1. So I squared equals -1. The imaginary unit squared is -1. So now you have a number. When you square it, you get a negative. What kind of number is it? It's imaginary. Okay, so now you can describe the square roots of negatives. For example, if you take the square root of -25, that's not a real number. because there is no real number that I can square it and get negative 25. Doesn't exist. But I can do a little finagling here and rewrite this. So negative 25 can be written as negative 1 times 25. That is true. And you have a property of square roots that says this. If I have the square root of a product, so I have the square root of two factors, a times b, I can write that as the product of the square roots. I can do that. That's a law. So a law in mathematics says that somebody before you has proved this to be true for every single number a and b, all of them. So you can multiply, you can take the square root of the product of a and b, and that's the same as the square root of a times the square root of b. And this is what we use to simplify radicals. All right, so back to our problem. If we have the square root of negative 1 times 25, then we can write that as the square root of negative 1 times the square root of 25. Well, by definition, the square root of negative 1 is the imaginary unit I. The square root of 25, well, what number do you square to get 25? That's 5. So the square root of 25 is 5. So you have I times 5, or 5i. So the square root of negative 25 is the imaginary number 5i. The imaginary number is the imaginary unit times some constant. All right. So the square root of negative 25, we can now define as an imaginary unit, imaginary number 5i. I'll spit it out. All right. So if we take the set of real numbers and we union them with that set we just defined, the set of imaginary numbers, we get the set of numbers called complex. And they're not complex because they're difficult. They're complex because they're the combination of the set of real numbers and the set of imaginary numbers. So real numbers are just numbers that you could represent on the number line. It's just a number. And imaginary numbers are all those numbers that have an I in them. So 1i, 2i, 10i, 50i, those are the imaginary units, imaginary numbers. Negative 70i, those are imaginary numbers. So if I join those together with a union, I get this set that's called complex. And the way we write that is a plus bi, the real part plus the imaginary part. So again, complex numbers are a combination of real numbers and imaginary numbers. So if we join those together, we got a real number a and an imaginary number bi, and we join those together, we get a complex number. Now, a and b are real numbers, and I is the imaginary unit. So this is the real part. And this is the imaginary number. And we join those with an addition or subtraction or whatever. And the standard form of the complex number is we write the real part first and then the imaginary number second. So we write real, imaginary in that order. And MyMathLab can be kind of particular about the way you write this. Okay? So here are some examples of complex numbers. Now, since the complex numbers are a union of the set of real numbers and the set of imaginary numbers, the set of real numbers is a subset of the set of complex numbers. So every real number is complex. Since the set of complex numbers is the union of the set of real numbers and the set of imaginary numbers, all imaginary numbers are also complex. Imaginary numbers are a subset of the set of complex numbers. All right, so each of these are examples of complex numbers. The first number is negative 4 plus 6i. So the real part of this complex number is the negative 4. The imaginary number is the 6i. So the imaginary part is the 6, and you're multiplying that times the imaginary unit I. So it's a combination of a real number and imaginary number. 2i is also complex. It's complex in the way that its real part is 0. So if the real part is 0 and you only have the imaginary part, you have an imaginary number. Imaginary numbers are also complex numbers. And then the last example, 3. 3 is a real number. There's no imaginary part there because the imaginary part is 0. So it's a real number, but it's also complex with its real part being, its real part being 3 and its imaginary part being 0. So every real number is also complex. Every imaginary number is also complex. Now, two complex numbers are equal to each other if and only if the real parts are identical and the imaginary parts are identical. So the real numbers have to be equivalent to each other, and then the imaginary numbers have to be equivalent to each other. All right, so since this is a number system, just like natural numbers, whole numbers, integers, rational, irrational, real are number systems, and we have 4 arithmetic operations that we can conduct on each of those number systems. We can add, subtract, multiply, and divide them. We can do the same thing with complex numbers. We can add them, we can subtract them, we can multiply them, and we can divide them. And to do that, we treat the complex number like it's a binomial, and we treat the I, the imaginary unit, like it's a variable. Okay, so how do we add complex numbers together? Just treat the I like it's an X, like it's a variable, and combine like terms. So the first problem I have here, I'm adding the two complex numbers, 5 minus 2i and 3 plus 3i. So if I were adding these and that I was an X, I would combine like terms. So I would combine the 5 and the 3, and I would combine the minus 2i and the plus 3i. And I would combine them just like I were adding constants and variables. So 5 and 3 is 8. Then I have negative 2i and 3i. Well, negative 2 plus 3 is 1. So I get 1i, which we can just write as 1 plus I. And again, when we're writing complex numbers, typically we write the real part first and the imaginary part second. That's standard form. And MyMathLab can be very picky about you writing the real part first. The real part comes first, the imaginary part comes second. All right, how do we subtract? Well, if the I were an X, we're going to remove the parentheses and then combine like terms. And you do the same thing here. But we're going to have to distribute that negative across because we're subtracting 12 minus I. So we're taking the complex number 2 plus 6i, and we're subtracting from it the complex number 12 minus I. So what do we get? When I distribute that negative across positive 12, I get negative 12. When I distribute that negative across the negative I get plus I. And then combine like terms. 2 minus 12 is at negative 10. And then 6i plus I is at 7i. All right. Now we can also multiply them. And how do you suppose you'd multiply them? So I got two products here. I'm multiplying 7i times 2 minus 9i. And then I'm going to multiply the two complex numbers, 5 plus 4i and 6 minus 7i. And how could you do that? What would you do? Well, you have a distributive law. And the distributive law applies to everything. It works for absolutely everything. When you see that distributive law, it matters not one iota what A, B, and C are. They can be anything, and the distributive law is going to work. Holds for absolutely anything. So I can distribute the 7i across. So what do I get? I get 7i times 2 minus, be sure you carry that minus down, 7i times 9i. Now what do I get? Well, I have 7i times 2. If that were an x, 7x times 2 would be 14x, so that's 14i. Minus, I have 7 times 9, that's 63. But I have I times I. I times I is I squared. Now, by definition, I squared, the imaginary unit squared, by definition is -1. So the imaginary unit squared is the real number -1. I squared, by definition, is -1. So I can make that substitution. Now, what happens in that second term? I have minus minus, that becomes plus. -6 minus 6 times -1 is plus 63. I said 6, 63. And then we need to rewrite that using the commutative law. We need to change the order. The real part needs to come first and the imaginary part second. All right. Well, how about the product in the second example? I have the product of the two complex numbers, 5 plus 4i and 6 minus 7i. Well, you know how to multiply binomials. We use FOIL. And FOIL is, again, just an acronym to help us use the distributive law. That's what it is. So what do we do first? Well, first would be what? 6 times 5, 5 times 6. And then we do outside. We have minus 5 times 7i. Now, the reason it's negative is because I'm going to have positive times negative. That's going to give me negative. So it's going to be 5 times 7i, and we're going to subtract that. Excuse me, got tickled. Then we're going to do inside. So I have 4i times 6, and that's going to be plus because both 4i and 6 are positive. And then I have last. What's last going to be? Well, I have a negative. 4 times -7 is going to give me negative 28, right? Well, I should probably write that out. 4 times 7. But I have I times I. I have an I in the first last term, and I have an I in the second number's last term. So I'm going to have I times I, which is I squared. Okay, now let's do a little simplifying. So 5 times 6 is 30. Minus 5 times 7i is minus 35i. 4i times 6 is 24i. Then I have minus 4 times 7 is minus 28 times I squared. But what's I squared? Again, I squared is -1. So I can make that substitution. And while I'm at it, I'm going to go ahead and combine the i's. -35 plus 24 is -11. Minus 28 times -1. I squared is defined to be -1. So I have 30 minus 11i plus 28. -28 times -1 is plus 28, or 58 minus 11i. Okay, so we can add, subtract, and multiply complex numbers. We can also divide them, but division is a little bit trickier. So we need to define what a conjugate is. All right, so a complex number is a combination of a real part and an imaginary part. So that's a complex number. The conjugate of a complex number is the same number, except you change the sign of the imaginary part. So the conjugate of this is 5 minus 2i. Those two numbers are conjugates. What's the only difference between a complex number and its conjugate is the sign of the imaginary part. That's the only difference. So if I have negative 3 plus 7i, its conjugate would be negative 3 minus 7i. So all you do is change the sign of the imaginary part. Well, what's really cool is what happens when you multiply a complex number by its conjugate. And we're going to do this in general. So we're going to multiply a plus bi times its conjugate, which is a minus bi. Okay? And we're going to FOIL this. So we're going to multiply a times a first. A times a is a squared. Now we're going to multiply outside. So I have a times minus bi. A times minus bi is going to give me minus abi. Then we're going to do inside. I have bi times a. That's going to be positive abi. And then we're going to do last. I have b times b, and it's going to be b times negative b. So it's going to be negative b times b, negative b squared. I times I. I times I is I squared. Now, the outside inside terms add to 0, which is what you should expect. Whenever you multiply a sum times a difference, the outside and inside add to 0. That's what happens. So what are you left with? You're left with a squared minus b squared times I squared. But what's I squared? I squared is negative 1 by definition. And what's minus b squared times negative 1? Well, that's plus b squared. So whenever you multiply, well, let's pause a minute. That's real. That's a real number. There's no i's anywhere. No i's. So whenever you multiply a complex number by its conjugate, the result you get is real. It's a real number. So we can utilize that, the fact that when we multiply a complex number by its conjugate, we get a real number to do division. Right? You have two formulas for this. Whenever you multiply a complex number by its conjugate, you get the sum of two squares. So when I multiply a plus bi times a minus bi, I get a squared plus b squared. Same is true for the next. If I multiply a minus bi times a plus bi, I get a squared plus b squared. So for example, if I take 2 plus 3i and I multiply it by its conjugate, what happens is outside inside is going to add to 0, and the second term is going to be negative 9i squared, or plus 9. So what I do is I take the first number and I square it. Then I take the second number, the number in front of the I, and I square that, and I add them together. That's all there is to it. Whenever you multiply a complex number by its conjugate, you get the sum of the two squares. So what's that, 13? Okay, so if I do this, let's do something different. Now, those are conjugates. Why are those conjugates? Because the only difference in the two is the sign on the imaginary part. The first complex number is negative 7 minus 5i. So the sign in front of the imaginary part is negative. It's negative 5i. The second number is identical, except the 5i is positive. So those are complex conjugates. And when I multiply a complex number by its conjugate, I take the first number and I square it. So I take the negative 7 and I square it. Negative 7 times negative 7 is 49. I take the second number, which is the 5, and I square it, 25, and I add that. That is all there is to it. Don't make this hard. So whatever that is that 74? So whenever you multiply a complex number by its conjugate, you get a real number. And that real number can be determined by taking the first number, the real part, and squaring it. Taking the imaginary part, so in this case, it's 5, and squaring it, and then adding those two things together. -7 squared is 49. 5 squared is 25. 25 and 49 is 74. And we utilize this to divide. So the goal of complex number division is to get rid of the complex number in the denominator. And I know I can force a complex number to be real by multiplying by its conjugate. Okay? So here is a division of complex numbers. We're taking the number 5 plus 4i, and we're dividing that by 4 minus I. And I can do that division by using conjugates. All right? So I know that if I multiply a complex number by its conjugate, I get a real number. So I can multiply the 4 minus I times 4 plus I, and I know that denominator will be a real number, which is what I want to do. Division by complex numbers, what I want to do is to get the denominator to be a real number, and I can do that by multiplying by its conjugate. Now, you know that I can't just do that. As soon as you did that, you've done something incredibly wrong. 1 is called the multiplicative identity. I love that word, multiplicative. Multiplicative. Okay, what's that mean? What's the multiplicative identity? Well, if I take any number, and I mean any number, real, complex, imaginary, it doesn't matter, any number, and I multiply it by 1, what happens? Not a thing. Correct? So if I multiply 2 by 1, I still get 2. If I multiply -1 million by 1, I still get -1 million. So the multiplicative identity is 1 because if I multiply any number by 1, I don't change the number. Now, I can change its form by multiplying by 1. So back in the day when you learned to add fractions, what if you want to change the form of that fraction so that the denominator is 6? So you're going to multiply by 2. That's how you're going to get that denominator to be 6. But you don't multiply by 2, you multiply by 2 over 2. Because what's 2 over 2? 1. So what you're doing is you're changing the form of the number, but you're not changing the number. 4 over 6 and 2 over 3 are the same number. Same number. So you can change its form. So I can do the same thing over here. I can change the form of that complex number by multiplying by 1. And what would the 1 that I multiply be? 4 plus I over 4 plus I. 4 plus I over 4 plus I. Any number that you divide by itself is 1, except 0. A over A is 1. A can be any number at all, any complex number. So if I multiply 5 plus 4i divided by 5 minus 4i by 4 plus I over 4 plus I, the denominator is going to be a real number. And then I'm going to be able to complete that division. So I'm going to carry out this multiplication. Now the numerator, I'm going to have to FOIL. The denominator, I can use the formula for. Okay, so when I multiply a complex number by its conjugate, those are conjugates because I deliberately picked the conjugate to multiply by. I take the first number, which is 4, and I square it. I add to it what's the coefficient? What's the number in front of the I? Well, it's 1. So I take the 1 and I square it. And this is always plus. Take the first coefficient, the first number, the real number part, and square it. Then I take the imaginary part, which in this case is 1, because the imaginary number is 1i, and I square it, and I add them together. Now the numerator, I'm going to have to FOIL. Okay, so let's see if we got my foiling skills. So I have 5 times 4 is 20. Then I have outside 5 times I, that would be 5i. Extend my division bar here. Then inside I have 4i times 4, is that 16i? And then last I have 4i times I, is that 4i squared? All right, so now let's do a little simplification. 5 and 16 is 21. I squared is -1. 4 squared plus 1 squared is 17. So now I have 20 plus 21i minus 4. 4 times -1 is -4 over 17, which is 16 plus 21i over 17. And let it catch up. MyMathLab does not want it written in that form. You know that if you have multiple terms being written over a single denominator, you can actually take each term in the numerator and write it over that denominator. So this is equivalent to 16 over 17 plus 21 over 17i. If you have A plus B over C, that's equivalent to A over C plus B over C. That's actually how you learned to add fractions back in the day. Because if you have 1/3 and 4/3, that's 1 plus 4 over 3, which is 5/3. That's how you learn to add fractions back in the 4th or 5th grade, wherever you learn to add fractions. So we can take the 16 plus 21i over 17 and write that as 16 17ths plus 21 17ths I. And that is the form that MyMathLab wants it in. Okay, so now there's nothing you can't do. Nothing. You can now deal with any numbers that come your way. Because you have real numbers, the numbers on the number line, and you have these imaginary numbers, which are the square roots and negatives. Combined, that gives you the complex numbers. So let's give you a definition of how to find an imaginary number. The principal square root of a negative number. So for any positive real number b, the principal square root of the negative number negative b is I square root b. So the square root of -16, which we looked at earlier, is I times the square root of 16. What's the square root of 16? Well, it's the number that you when you multiply it times itself, you get 16, so that's 4. So this is 4i. The square root of -36, the square root of a negative is going to give me an imaginary number. The square root of 36 is 6. So the square root of -36 is 6i. The square root of -49, it's going to be imaginary. So we need an imaginary unit. What number do I square to get 49? 7. The square root of -121 is going to be imaginary because we're taking the square root of a negative. What do I multiply times itself to get 121? Well, what's the square root of 121? It's 11. So now you can take the square root of any number. The square root of 25 If it's positive, it's just 5. But the square root of negative 25 is the imaginary number 5i. Okay. So how do you deal with this? All right, so if you own the TI-30SX calculator, the TI-36SX calculator does simplify radicals for you. The TI-84 does not simplify radicals. So what do we mean by simplifying radicals? Now, this has some legacy to it, why we simplify radicals. Part of it has to do with the way we used to have to calculate square roots. But you need to know how to do this to simplify things when you get to higher mathematics. Again, you're in college algebra, which means I'm assuming you're a STEM student, which means you're probably going to go on in mathematics. So you're going to have to simplify radicals along the line somewhere. So what's this mean to simplify a radical? Well, you look at this thing under the radical, which has a name. We call it the radicand. So the thing underneath the root symbol is the radicand. So you're taking the square root of 45. Well, there is no number you can multiply times itself perfectly and get 45. So the square root of 45 is an irrational number. It's a decimal that doesn't repeat. However, 45 does have a factor that's a perfect square. You can write 45 as 9 times 5. So now you've written 45 as a product of a perfect square and another number. So now you have a property which we talked about earlier, that if you have the square root of a product, you can write that as the product of the square roots. You can do that. That's a law. And then you know what the square root of 9 is. What's the square root of 9? Well, it's the number when you multiply it by itself, you get 9. So the square root of 9 is 3. Square root of 5, some irrational number. So the square root of 45 is the same thing as 3 times the square root of 5. And you can take your calculator out and show that's true. Take the square root of 45 and get you a decimal approximation. Then take 3 times the square root of 5 and get a decimal approximation. They're the same number, exactly the same number. So I don't know, let's do another one. Can I think of one? Now, 128 is not a perfect square because if you take your calculator out and you take the square root of 128, you get a decimal. However, 128 does have a factor that's a perfect square. And it's 64. 64 times 2 is 128. So that, by definition, is the square root of 64 times the square root of 2. Square root of 64, I can calculate. That's 8. Square root of 2 is irrational. So I'm going to leave that in terms of the radical. So 8 times the square root of 2, exactly the same number as the square root of 128. They're exactly the same value. Okay? If I did that right. Is that right? Since I just made it up out of my head, you have to check me. Okay, so you can do the same thing if you have square roots of negatives. Same thing. Okay, so we're going to write negative 27 as a product of something I can take the square root of, an imaginary number, and whatever's left over. So I can write this as negative 9 times 3. Negative 9 times 3 is negative 27. And I can write negative 48 as negative 16 times 3. I can do that. So now I can rewrite this. The square root of negative 9 is 3i. The square root of negative 16 is 4i. 4i times 4i gives me negative 16. And now you can see that you can actually combine these. I have 3i square root 3 and 4i square root 3. So how many I square root 3's do I have? I have 7 of them. So I have 7i square root 3. So I got 3i's square root 3's over here and 4i square root 3's over here. How many total do I have? I have 7 of them. 7i square root 3. Now, how do I multiply down here at the bottom? Well, multiplication, we're going to FOIL it. But I am going to change this to I square root 3. Because the square root of negative 3 is, by definition, I times the square root of 3. That is by definition that we got on a couple of slides earlier. So now I can FOIL this. Now, you got a lot of negatives, so you need to be careful with all those negatives because you got a lot of them. So just be really, really careful when you FOIL this. So you have negative 2 times negative 2. Negative 2 times negative 2 is positive 4. Then I have negative 2 times negative I square root 3. Well, that will give me 2. Square root 3. Well, that will give me 2. Okay. Now I'm going to do inside. Again, I'm going to have negative times negative. So that's going to be plus. And what do I have? I got a 2, an I, and a square root of 3. And then I'm going to do last. Negative times negative is going to give me plus. I have I times I, which is I squared. But what's the square root of 3 times the square root of 3? Because what I'm multiplying together there is I square root 3 and I square root 3. Well, I times I is I squared. But the square root of 3 times the square root of 3 is what? Well, that's the square root of 3 times 3, which is the square root of 9. So that is 3. So when you square a square root, you just get the radicand. So this is I squared times 3. And now we can simplify that. I got 4. I got 2i square root 3 and 2i square root 3. So how many I square root 3's do I have? I have 4 of those. And then I have I squared times 3. I squared by definition is the one number negative 1. So that's negative 3. So I end up with 4 minus 3 is 1. That's about as complicated, as complex number multiplication. That's probably as complicated as you can possibly get. But again, you're foiling, and you know how to FOIL. FOIL is an acronym to help you keep track of your distributive law. So you multiply first terms, negative 2 times negative 2. Negative 2 times negative 2 is positive 4. Outside, you have negative 2 times negative I square root 3. That gives you plus 2i square root 3. Inside, negative times negative is going to give you positive. You've got I square root 3 times 2, 2i square root 3. Then you have negative I square root 3 times negative I square root 3. That's going to give you a positive. I times I is I squared. The square root of 3 times the square root of 3 is the number 3. Take your calculator out and show to yourself that that's true. The square root of 3 times the square root of 3 is 3. Then you can combine like terms. I squared, by definition, is the number negative 1. All right, are there any questions? No? Well, if there are any questions, I'm going to end the meeting, and we will be back again on Thursday via Zoom. The 11 o'clock class, let me show you how to find those. Let me stop this share. Let me share up here, do a quick screen share. So the easiest way to get to the Zoom meeting is to, again, go to your course. This is my office hours, which I am going to start at 2 o'clock. So in 15 minutes, I start this meeting. But to find the classroom meetings, maybe I should call this class Zoom meetings or something. Click on that link, and that will take you to the internet connection was unstable. That'll take you to the list of meetings for this class. All right, are there any questions? All right, we will talk to you Thursday. Have a good rest of your day.